Okay, good morning and welcome to our pre-flight press conference with the flight crew from Space Shuttle Mission 51L, due to go up in January. I'll introduce the commander of the flight, Dick Scobie, on the left of the podium here, and Dick will introduce the rest of the crew.
Pleasure being here with you all this morning. This good-looking group off to my right, I'd like to introduce them one at a time by specialty, and then I would like each one of them to say a little bit about what they're going to do on the flight. So without further ado, Elson Onizuka is our expert on the Tracking Data Relay Satellite, the inertial upper stage, our largest payload on board. Ron McNair is our expert on the Spartan Halley, the Comet Research Satellite we're carrying on board that we're going to put out over the side for a couple days and pick up. Mike Smith, our pilot, who also backs me up on everything I do. He's also an expert in rendezvous, prox ops, and systems. Judy Resnick, who's our flight engineer, probably one of the most knowledgeable people on systems on the orbiter in the astronaut office, so she's a real asset to the crew. She is also our remote manipulator system operator, so she's a crane operator on the side. Greg Jarvis, who's one of our payload specialists. Greg has a flight dynamics experiment on board he'll talk to you about. It's fairly colorful, and it's a nice experiment to be performed on board the orbiter during the whole mission. And of course, Krista McAuliffe, our teacher in space, who will be doing teacher activities the whole flight. So first off, I'd like to start off with Ellen. We'll just run down the line and everybody talk a little bit about what they do on the mission.
Well, the Tracking and Data Relay Satellite, commonly referred to as TDRS, is being launched on this mission using a large inertial upper stage booster. It's a solid rocket booster weighing just under 40,000 pounds. With the satellite itself, we have a package of approximately 45,000 pounds being deployed from the shuttle. This is the second of the TDRS satellites to be deployed. With this satellite on orbit, we will then have near global coverage using this satellite, which we will eventually place somewhere over the Pacific, and the satellite that currently is on station northwest of Brazil. We will be able to have almost complete global coverage for shuttle operations. The TDRS mission itself is quite involved. We will start our initial upper stage checkouts beginning about 1 hour and 40 minutes into the mission. Working through the rest of the activities, our intent is to deploy this satellite approximately 10 hours into the mission. The satellite is presently undergoing tests at the Kennedy Space Center. The booster has completed its testing, and the satellite and booster will go through a final test at the launch pad sometime in early January, and we hope to be launching on schedule, on time.
The Spartan Halley spacecraft has the distinction of being one of the first in a series of free-flying satellites that will observe the comet Halley. The Spartan has flown on a previous mission. It carries many scientific packages, but the Halley scientific package will be one carrying instruments that will enable the spacecraft to determine where it is in the universe, where the comet must be, and aim its sensors at the comet in order to make measurements. The Spartan Halley will be deployed from the payload bay using the manipulator arm, and Judy will tell you more about that. And the orbiter will back away and return to retrieve it several days later, which Mike and Dick will be performing those maneuvers. But while the satellite is out there, we'll use its sun sensors to look at the sun. Then we'll use its star trackers to find a fixed star. And using that information and the data that I will be loading into it, Elle and I will be doing the Spartan preparation, then the Spartan will be able to fire its jets to maneuver around to where the comet, a small dot in the universe, and make very precise measurements. Now, comets are very much in the news now. I don't need to tell you much about the comets, except that they happen to be remnants of the creation of the universe, the origins of the universe, frozen gases of various types of gases. And scientists are interested in knowing just what are the components of a comet. What are the constituent gases that makes up the comet? And from this, we can get some idea about the origins of the universe, and these type of studies can sometimes change the way you think about things. So consequently, we look forward to this experiment. It's not just a satellite that we kick out and forget about it, but it affords us, the crew, the opportunity to do many different things. A deploy sequence, We get to do some arm operations. We get to do some rendezvous and proximity operations. And it's an exciting one for us as well as for scientists at the University of Colorado, who happen to be the principal investigators. So Spartan, the Common Halley, we'll learn a little bit about it, a great deal about it, and enjoy doing it in the process.
Well, as Ron said, the Spartan is a free flyer, and that means that we're going to have to do some proximity operations and also a rendezvous to pick it up after it does its mission. And on flight day 3, Judy will put the satellite in the proper position over the payload bay, and we will position the orbiter in its proper attitude, and we'll release the Spartan late in the day, around 7 or 8 o'clock Houston time. Once the Spartan is released, we station keep on the satellite for about 10 minutes. We then do, while we're station keeping on it, the Spartan goes through some of its checkout maneuvers to make sure that its attitude control system is going to work correctly. If it doesn't work correctly, we'll pick the satellite back up and put it back in the bay, but assuming that it works, everything checks out correctly, then we'll do a burn to separate from the satellite. It takes us up and over the satellite, and then we basically just drift away from the satellite for 16 orbits, or about 24 hours. 24 hours later, we do a small burn that starts us drifting back towards the Spartan Halley satellite, and then we sleep for about 10 revs while we drift back towards the satellite. Then when we get up on flight day 5, we start our rendezvous maneuvers, a series of burns that brings us up about 500 feet in front of the satellite. At that point, Dick will fly the shuttle up to within about 35 feet, putting the Spartan Halley right over the payload bay, and Judy will pick up the satellite with a remote manipulator arm. Just before we get to the 500 feet from the satellite will turn on its lights and also maneuver to the proper attitude so that Judy can pick it up with the arm.
And I'll tell you a little bit about the Spartan and operating it with the arm. Spartan is a box that's about 4 by 4 by 4 feet. When it sits in the cargo bay, if you can imagine that I'm in the cockpit looking aft, it sits in the cargo bay like this, and the arm comes out and picks it up on its grapple fixture like so, and will actually maneuver it so that its sun sensor is pointing towards the sun, which is off the tail, and we'll let it out of the orbiter more or less like this, and it will do its pointing, as Ron said, and we will fly away from it. And when we come back to retrieve it, once again we'll have the arm up, and it will be coming at us more or less like this, and hopefully with the plane in the right plane where the grapple fixture and the arm are lined up, and just grab a hold of it and put it back down in the bay. We're going to use the arm for a couple of other things on the mission, not quite as extensive operations as we do with the Spartan,
but we are going to use it on day 1 to take a look at the firing of the inertial upper stage's first rocket motor, which happens about an hour after we let it out.
We'll actually position the arm so that the wrist camera can monitor the ignition of that burn and watch it through its duration. We'll also use the arm before we deploy the Spartan to actually do a little survey of it in the payload bay to check that its experiment doors are in the proper configuration, and check the sunshade and the baffle area and make sure there's no ice or dust on it so that the experiment will operate properly. The other thing that I'm doing for the mission is being the third seat for ascent and entry. It's really the backseat driver for Mike and Dick. I'll just help them with nominal and any off-nominal procedures that they have. I don't throw any of the switches. They do all the switch throws, but I sort of keep track of what's going on.
I'll be conducting a set of experiments that investigate the effects of zero gravity on fluid motion. The experiment uses vessels that are scale models of propellant tanks that we use in the satellites built by Hughes. The first set of experiments document the fluid motion in both a spherical and conospherical tank. The second set of experiments uses a model of the spacecraft to investigate the stability of Frisbee dynamics with various amounts of fraction fill of liquid in the tanks. The third set of experiments uses the same spacecraft model in a free-flying mode in the mid-deck locker to gather data in a sustained zero-gravity environment to correlate that data with data that we've used
we obtain using drop test data in the laboratory.
And as the first space participant, I'd just like to say that I am very delighted to be part of this crew. Everybody's been wonderful in making me feel a part of this mission. I'll be teaching 2 lessons from the shuttle, and I was amazed to find out how much crew participation I needed for the 2 lessons. Everybody's going to be involved in the field trip through the shuttle, either trying to stay out of the way so that they can get a good camera shot, or actually helping me out or using the camera. So it's a whole crew activity when the lessons are filmed. The 2 lessons will be downlinked live. And I think it's going to be very exciting for kids to be able to turn on the TV and see the teacher teaching from space. The first is going to be a field trip through the shuttle, and it will start up on the flight deck. And after I introduce the commander and the pilot and talk a little bit about the flight deck, I'll be floating down into the middeck and dealing with all of the things that have to take place because of a weightless environment. Why do you have to have things stowed a certain way, or the exercise that has to be done on board the shuttle, or the galley that is used and how things are a little different, or the sleep sack, or the bathroom facilities. And then the second lesson is why are we in space, starting with the quantum leaps that we have made from the Wright brothers' flight up to the space station, which is our future in space. A lot of people, when I first started this whole venture and talking to them, really didn't have a good idea of some of the experiments that took place on board the shuttle or some of the satellites that were launched. So I'm hoping to bring that out in the second lesson. There'll also be some demonstrations that I'm going to be doing, and these aren't going to be live, but they will be brought back in 16mm film and will be scripted and sent out to the schools at a later date. When the 10 of us met as the 10 finalists in Washington, D.C. in August, we realized that we wanted something very visual that students could do in the classroom and look and see how it happened that a magnet, for example, was reacting in a weightless environment, and how it happened that that magnet reacted in a gravity environment. So there's going to be one on magnetism. The demonstrations, one of them is going to be on magnetism, and we've got a wonderful 3-dimensional magnet that we took up in the KC-135, and it just worked beautifully. So we're very excited about that. There's going to be one on chromatography, one on simple machines, just so that the students have an idea of whether simple machines would ever have been developed in space, because it certainly helps us do work on Earth. Another one on hydroponics. We're going to be doing something on Newton's laws, because a lot of teachers say it's very difficult to teach Newton's laws when you have gravity to contend with down here on Earth. And the last one will be on effervescence, just to see how bubbles react. So I'm quite excited in being part of this wonderful mission.
Okay, if that's the summary from all the crew members, we'll go ahead and begin questions, starting here from Houston and then from the other centers. If we have questions to start with in Houston, we'll pass the microphone around, and when the microphone gets to you, please state your name and affiliation. Carlos?
Carlos Byers, Houston Chronicle. How far are you going to get away from Spartan Halley? What's
About 95 miles is the farthest that we'll get.
We have other questions here in Houston. Yeah, Paul.
You said the lights are going to come on the Spartan Halley. Is the rendezvous or the station keeping at 35 feet can be in darkness, or is that timed to occur after sunrise?
No, it's the we are on the V-bar. In other words, 500 feet in front of the satellite, just at sunrise, just a little bit after sunrise, and the final portion of the approach will be done in daylight. We should arrive at the pickup point at around orbital noon.
Okay, with the lights on, when do you expect the first sighting of it as you're moving in? What distance? Any idea?
Maybe Dick can answer that since he's done it before.
The lights won't be on until after daylight, so the Spartan, one of the problems, it's not a problem, but the way the Spartan is programmed, it has an onboard computer that just starts at a time and it just runs its program, and there's no outside interference with that program. So it's programmed to turn on the lights and maneuver to an attitude at a certain time, and the way it's programmed to maneuver right now, we will be up on the V-bar when the lights come on, which is already daylight, so the lights won't help us find it. But we have a lot of satellites without running lights, so we don't need the lights.
Okay, but the lights then are not designed to help in rendezvous. They're just
Well, they are originally, but the specific program that the Halley part of the Spartan has on it doesn't allow them to be used for that on this particular mission. It'll also maneuver to its attitude right after we get on the V-bar.
There are reflectors along the bottom edges of it, and if we have the payload bay lights on, we will probably be able to, as it gets closer, even if the lights aren't on, be able to see. They're like bicycle-type reflectors.
Okay, did we have one right here? Yeah.
Hi, I'm Sean Wickham from the Union Leader. I have a question for Krista. Could you talk a little bit about your visions of the future in education as it relates to your enthusiasm for the space program? I know you know that space is something that we have to contend with as a future career, and that's sort of an idea.
Well, there's a couple of messages that hopefully I'll be able to bring back after this mission, and one is that I think NASA has alluded to that, obviously, in starting their space participant program, but just the message that space is for everybody. That's a new world out there, a new frontier, and that there are a lot of people who we have in our classrooms who are going to be living and working in space. And the second one is that there are so many support personnel involved with the launching of the space shuttle. Especially being from the Northeast and away from centers, we tend to forget that it's not just a small group that decide to launch the space shuttle, get in it, and do their experiments and come back. That there are so many other people involved in the aerospace industry. So I'm hoping that that generates a lot of enthusiasm in education for the space program.
Okay, others. Carlos, did you have one?
I thought I did. Yeah, Greg, could you tell us a little bit more about your experiments, please?
Let's see, the first set is we're trying to look at the general motion of fluid in both a sphere and a conosphere. Spheres and conospheres are the kinds of tanks we use in all our huge satellites. The first part of the experiment is just to see if it's affixed to the mid-deck lockers, to see if the bubble in the tanks has a specific position, or does it kind of move around anywhere. The second one is to take a look and see how long it takes for the fluid in the spinning tanks to come in equilibrium with the tanks. And we'll do that for various amounts of fraction fill in the tanks to see if there is any difference for more or less liquid. The Frisbee deployment, we're going to do that for both a 4-tank spherical module and a Centerline tank. The 4 tanks are typical of the older Hughes satellites, and the Centerline more fits in the propulsion cavity quite a bit better. And so we're looking for data to see if as we remove fluid from the tanks, if it affects the deployment. Currently, we fill the tanks all the way full to minimize the amount of fuel slosh in the tanks. And the second one, the last experiment, is to see how thank you. A little bit here. The Frisbee, this is the Centerline tank module, and this is the 4-tank module. And what will happen is that it's spring-loaded on the side, much like the LESAT spacecraft. It will remove fluid from this, and we expect it to deploy up in this mode like this up here. And we'll remove fluid to see how that affects the dynamics, if it does affect the dynamics. And what we've done in the past is to fill this all the way full so that it will not have any effect. The last set of experiments, we won't use this cradle anymore, but the spacecraft will be free-floating and spinning at about 100 RPM in front of the mid-deck lockers. And we have a little transmission system here of light-emitting diodes, and we'll be telemetering back to a small receiver located in the mid-deck accelerometer data. And what we're trying to do here is, as we remove liquid from the tank, to see if, as the spacecraft, as the model spins down, how long it takes to destabilize. Currently on our vehicles, and we always do, we continue to fire the jets to keep it stabilized. And so we're kind of wondering, for academic reasons and in correlation data, how as we remove fuel, as a spacecraft would go through its normal mission life, how the dynamics are changing.
Okay, you had one back over here, I believe.
Well, I had a question for Krista. So far, what's been the most rigorous part of your training? And I have a follow-up, too.
Oh, that's hard to say. A lot of the training is not, it's not physically rigorous. Mentally it is, because you're trying to learn all of this information to get yourself ready to go on board the shuttle. So there's an awful lot of information that I've been trying to make sure I have, so that I will know, for example, enough about the habitability systems so that I'll be able to be kind of self-sufficient when I'm on board the shuttle, and that's very important because the crew's going to be very busy. I also want to know what's happening on every day so that I will know kind of where to position myself and what's going on, if I can be of any help. So there's been an awful lot of learning that's been taking place. Probably one of the hardest things that has happened to me this year in trying to just get adjusted is that I'm no longer in school. I'm a student again, and full-time, and that is a big change from the last few years because I've been teaching, but also being so far away from my family, and this is a year commitment, and that's been probably one of the hardest adjustments I've had to make.
One other thing, there'll be other professions going into space, and I wonder if you can offer any advice to any of those future participants.
Did you like the journalists in
Well, for
space?
instance, journalists in space, or no, I mean just generally. Do you have any?
Well, I was delighted that a teacher was chosen as the first space participant because there are so many of us who have daily contact with people, and that was a very exciting thing for me to think that teachers were finally recognized as the good communicators that they are, and that they reach so many students. I mean, there's 2.5 million teachers in the United States. When you think of the daily contact, I mean, the impact that we have across the board, if you get teachers excited about something, is just phenomenal. For everybody else, just the same thing that I did when I looked at that application and thought, oh, it's so big, and this is something I really want to do, and just to try. And I'm hoping that everybody out there who decides to go for the journalist in space or the poet in space or whatever the other categories are, is that you just push yourself to get through that application, because you're not in the game unless you get that application mailed off. So I'm hoping that there's going to be probably more people down the road who are going to apply for this. And when you think of the future, there's going to be people flying in space, and it's going to be those kids that are in our classrooms. So it's a wonderful, wonderful thought.
Okay. Let's take one from Paul. Did you still have one?
Yeah. Greg, these fluid dynamics tests, the tanks and everything that you have there, are these just a random design, or are they specifically modeled on so far as mass distribution is concerned, to existing and proposed spacecraft?
Let's see. First, to answer the first question is they are scale models, and the mass properties of this particular vehicle are the same as LESAT. The Centerline tank is for a new vehicle that we're looking at. It's called the multi-mission bus, and you can see that because of the design of the tank, it fits in the aft end of the spacecraft quite nicely, as opposed to being on the outboard side. So it's a good utilization of space. So this will probably be the wave of the future in terms of propulsion for us.
Okay, we'll take one from Stephen Govain, and then we'll hit the other NASA centers.
Stephen Govain, Channel 13 for Ron. There are going to be other nations sending spacecraft through the tail of Halley's Comet. What do we think that we might learn that other nations might not be learning with Spartan?
The significance of our Spartan is the timing. The other nations will be sending their spacecraft through the tail of Comet once the spacecraft has gone around the sun, is on its outbound leg of its journey. Of course, the greatest scientific payoff occurs when the comet is closest to the sun. That's where the heating is greatest. That's where the ice will be thawed and gases will spew out, which creates the tail. Well, we will be looking at the spacecraft when it's closest to the sun, closer than any of the others. Consequently, the scientific payoff will be greater at that point. The problem with observing it when it's very, very close to the sun is very obvious. You're looking at the sun and you can't see the thing, particularly the way the comet is lined up with the Earth and the sun at the moment. So we have the Halley has a special sunshade developed to cut down the sun, some 10 to the 14. That's a huge number. It will really cut down sunlight and enable us to look at the comet when it's very, very close to the sun, and that's the advantage we have. We will perhaps see some of the phenomena as a result of the heating that perhaps you may not see once the comet is a little further away.
Okay, well, we'll take questions now from NASA headquarters.
Albert Salestead, Baltimore Sun, for Ms. McAuliffe. Would you kindly repeat again what your schedule is? I'm unclear as to which of your demonstrations or lessons will be sent down live and which ones will be on film. And if you could, what days will you do these?
Right now, the 2 live lessons will be sent down on the 6th day of the mission. I believe the time has changed a little bit. Right now it's going to be 11:30 Eastern Standard Time and 1:30, and that could move as the time for the launch moves around a little bit. The other demonstrations will be done from day 2 on whenever there is time in the crew activity plan for me to do these without having a problem with other activities that are going on board. And those will be scripted when I'm back and will be available to schools after NASA puts them together on a 60mm film and does the scripting to them. So I'm not sure exactly when those will be available.
This is Craig Cavalt with Aviation Week, and I'll direct this to Ron and Mike and JR. Please chime in if applicable. I'm sure there's some way you can use the orbiter to point Spartan Halley if it malfunctions and can't work out there on its own, but I'm not quite sure where that would come into play. Can you describe a little bit, is it when you first deploy it, if it does not start its cycle, you would go get it again with the arm and then try and do some orbiter pointing, and how good can you function with the orbiter pointing that spacecraft?
The scenario you just mentioned is feasible if we deploy the Spartan and this verification maneuver does not confirm that the Spartan attitude control system is functioning right. We will bring it in, investigate it, and possibly keep the Spartan in the payload bay and use the orbiter as a pointer. Some other possible scenarios are if the arm has a malfunction that it cannot deploy the Spartan, or some orbiter problems, or problems with the Spartan latching mechanism. All of these will cause us to keep the Spartan in the payload bay, and we have a mode of operation we call the in-the-bay mode, where we keep the Spartan in the payload bay. We open up the doors to expose the spectrometers to the space environment, and Mike and Dick will point the orbiter using some data that the ground will give to us, and the Spartan can go through its sequence using the orbiter as a pointer instead of its onboard instruments. And this can be done quite well. We have a slit on the spectrometers, and we have a system where we will scan the comet using a raster scan, where we form a raster pattern, and we'll also point the orbiter at the comet and roll the orbiter such that the slit sweeps out a circle over the comet to make sure that we get some type of data. So this could be done as a backup contingency mode. We could do this and still accomplish the mission quite successfully.
Are you taking your saxophone this time, Ron?
Well, I'd like to, but I don't think I'll be able to do it this time.
Moving down to Mrs. McAuliffe, you know, better part of 10 years ago, the Skylab astronauts worked what they called Classroom in Space and made a number of tapes. Have you reviewed those, and have they been any help to you?
The tapes that have been made have been a great deal of help because for positioning the camera, perhaps not as much in the Skylab mission, but the ones the small field trips that have been done on previous missions. Barbara and I were able to review those, and it gave us a better idea of what worked and what didn't work, what showed up best, because we only have a short period of time, so we want this to be as visual as possible and to have students and the public be able to see what's going on. So that has provided wonderful information for us.
Kind of a big picture thing here for you as well. If we can describe you as more or less the gal off the street, what do you know now about the U.S. space program that you didn't a year ago?
again, being from Concord, New Hampshire, not being near a space center, I was approaching incorporating space education in my teaching using the resources that I had, which were fairly limited, and doing a historical perspective, because that's what I teach. I do teach history. I do teach social studies. Now I kind of feel like I've got the tip of the iceberg down, but there's this much information that I wasn't even aware of. So it's been a wonderful learning experience for me, and just knowing all the resources has been great, because I've been able to send a lot of bibliographies back to teachers, and they've been contacting NASA centers. So there's a good ripple effect happening right now, getting that information out to the public.
That's all from headquarters.
Okay, we'll take questions from KSC.
Catherine Smith, Channel 9 in Orlando. A couple of questions. First for the commander. They dedicated your pad that you're going to be flying out of here today. How do you feel about being the first crew to go out of Pad B?
Oh, it's nice being a first on anything, but we're not really the first out of Pad B, because there were some Apollo launches out there, but we're the first shuttle out of Pad B. And it's, I guess our only consternation about that is anytime you dedicate a new facility like that, there are always startup problems, and so we're watching what's going on at the Cape to make sure that it doesn't delay our launch or anything. But right now they seem to have everything in hand, and it looks very, very well for getting off on the 22nd.
Well, you said you've had so much fun training. Are you going to feel any kind of a letdown when your year's over and you go back to teaching?
No, I don't think so. I see this as an extraordinary opportunity and a wonderful year out of what I've normally been doing, but I think it's just going to enhance the teaching that I do, get the students more excited about their future, which is important.
This is Jay Barbary with NBC. I have two questions for Krista. First, Krista, could you tell us, some dumb old southern boy like me, how do you pronounce your last name? I keep hearing it McAuliffe and McAuliffe. How do you pronounce it, with a heavy C or A?
It's McCall with an IF on the end, so it's McAuliffe. When my husband was in the service, we would often go into the medical facilities or wherever else we were going, and we would be called by number or name. And it would be great, because you'd have, the Smiths and the Jones and everybody else, and all of a sudden you'd hear number 387. And I always knew it was me, but it is McAuliffe.
You. And may I ask you also, if you achieve what you hope to achieve in space with your teaching, what do you think you will accomplish, or what are you trying to accomplish?
Well, repeating what I had said before, I do think that it's going to open up the idea that space is for everybody, and that's very important. I feel a great responsibility and excitement this year that I'm representing my profession. It's something that a lot of people don't have an opportunity to do, and I'm hoping that this is going to elevate the teaching profession in the eyes of the public and of those potential teachers out there. And hopefully one of the maybe secondary objectives of this is that students are going to be looking at me and perhaps thinking of going into teaching as a profession. Right now we are in a teaching shortage position in the United States, and I'm hoping that more students will look at this as a wonderful profession and that they will choose to be teachers.
One follow-up. What do you hope the students that participate in your teaching from space will learn?
More about what happens on board the shuttle, because I don't think the general public is aware of that. Here, perhaps you are, because you're near a center and a lot of parents and friends are involved in the space industry. When you get into an area that's not near a center, that doesn't happen. People actually, adults have asked me, how many stops is that shuttle going to make? Bring me back a moon rock. And I don't think they were saying this because they were totally ignorant. It was just that information hasn't gotten out to them. So I'm hoping as more and more people look at this program, they'll be aware of what actually goes on in space.
No more questions, Kate.
Okay, we'll take one or two final questions here in Houston if we have anyone who hasn't had an opportunity to ask a question yet. And seeing none, we'll conclude the press conference. I would like to ask everyone to stay back from the podium for about 2 minutes so the still photographers can get a couple of pictures, and then we'll head on out. Thank you very much for coming out today.